Our next presentation is RoVista Plus, mapping real ROV deployments, dependencies, and delays. I'd like to introduce TJ Chung, who will be presenting RoVista Plus, mapping real ROV deployments, dependencies, and delays. TJ is an associate professor at Virginia Tech and traveled from Blacksburg, Virginia to join us today. This is TJ's second time presenting at NANOG. TJ's first talk at NANOG was called RoVista, Measuring and Understanding the Route Origin Validation in RPKI at NANOG 90 back in Charlotte in 2024. Welcome back to NANOG, TJ. It's a pleasure to have you back with us today. Want to come up?
Yep. This is not the first slide. Yeah.
I think we can go back.
Yep. All right. Thank you.
You can go back with that one right there.
This one or?
That should go back. Oh, there it is.
All right. Hello, everyone. First of all, thank you for staying with me. All right. Let me start it. So my name is TJ from CS department at Virginia Tech. Today, I'd like to talk about RPKI, ROV. So yesterday there was a talk about ROA. This talk is the other perspective, which is about validation. So in RPKI, there are two perspectives. The first one is, let's say your network operators, you wanted to secure your IP prefixes. To do that, you need to publish an object called ROA. And then you publish it, and then you upload it to a publication point managed by RIR's repository. And the other perspective is routers, network operators, to validate incoming BGP announcements. They have to download those objects from repository, validate it, and then create a list of validated payload called VIPs. And then using that, you can validate incoming BGP announcements. So there are two questions. The first one is, how do network operators use RPKI to claim their IP prefixes? And the other one is, how do network operators also use RPKI to validate incoming BGP announcements for security purposes? So answering the first question is relatively easy because what you can do is you can download all the objects from the repository and then check the status of ROA to see how many IP prefixes are covered by ROA. However, answering the second question is relatively hard because let's say if I want to validate whether your network does ROV validation, I don't have any access to your routers, right? So that is why the second problem is really challenging. Because of this issue, there have been lots of approaches to answer this question in a collective manner. The first one is isbgpsafeyet.com. This platform is managed by Cloudflare. So how it works is really simple. When you go to the web page and click the test your ISP button, what it does is it requests two different contents, two different domain name. One is a valid.rpki, which is mapped to valid ROA. And then the other one is invalid one. So let's say you're in your home, so you test your ISPs and go to the web page, test your ISP button, click the button. And if you can download both of the contents, it means your ISP didn't do the validation at all. However, if you can only fetch the valid.rpki stuff, then it means your ISP filtered that out, the invalid announcement, or your upstream providers filtered this incoming invalid BGP announcement, which is good. Another one is because it is really hard to understand the whole RPKI ROV policy. So network operators often manage a collective spreadsheet. So they put their policy on this spreadsheet, say, hey, I don't do the validation for the traffic coming from my customer traffic or something like that. Or we often rely on official blog posts or mailing list, not on mailing list or something like that. However, this approach so far was not scalable. So I presented this work in NANOG 90. The tool name is RoVista, measuring RPKI ROV status at scale. So I used two techniques. The first one is we developed a technique that measures connectivity between two remote end hosts that I don't have any control. So how this technique works is we can pick a host, remote end host, And then we send the packet to the other end host, and we can tell whether this end host can send the packet to the other one. And the other one is, we noted that there have been lots of RPKI invalid prefixes in the while because of some misconfiguration. So combining these two together, what we tested was, we pick let's say I'm interested in a 1 AS. Then we find some network host in that AS, and we make that host send the ping to another host in RPKI invalid prefixes. So if that host can send the ping, can send the packet to another host in RPKI invalid prefixes, it means that AS doesn't do the RPKI validation. So using this technique, we've been running a platform, RoVista.netsecure.org, since early 2000. And it shows you can type your ASN in our platform to tell whether your network does ROV or not. So this platform works well. However, we had two limitations. The first one is visibility. Because our platform, the methodology is data plane based methodology, so we never know if some network does ROV, seems to validate ROV, then we never know whether it is because of that network deployed ROV by themselves, or whether it is due to their upstream providers. The second challenge we faced was, when we started this measurement in 2022, at the time, ROV was not that deployed well. So in RPKI in the while, invalid prefixes in the while, at the time there were like 50 or 60 prefixes every day. So there are lots of prefixes we can measure. However, these days, network operators actively deployed ROV. So this RPKI invalid prefixes dropped significantly. So this day, we can only measure like 2 or 3 prefixes. Because of that, we developed a new solution called RoVista Plus. But before introducing this new platform, I would like to talk about ROV ecosystem, how this ecosystem works. So there are 5 publication points, mainly managed by RIRs. And then if you're using your own publication point, so-called delegated RPKI model, then you can run your own publication point, and then you publish your RPKI objects like ROAs and etc. And then the relying parties have to fetch all RPKI objects from all publication points. And then they do the validation, they publish VRPs, and then network operators, ASes, can use this specific protocol to fetch these VRPs, validated RPKI prefixes. So we use this methodology. So we run our own publication point, and also we own our ASN number and IP prefixes, which means all the relying parties have to come to our publication points to fetch ROAs. And then there must be relying parties come to our network, and also ASs using RPKI go to their relying parties to fetch VRPs. So now we run our own network, and also we announce these prefixes mapped to our own ASN. However, when we create ROAs, we intentionally create 2 different ROAs, not just a static ROA. The first one is test ROA associated with another ASN, which we do not own. And the second one is control ROA associated with our own ASN. So here is the interesting part. So let's say we want to measure this relying party 1. Then when they come to our own publication point and asking for ROAs, we return this test ROAs to all the other relying parties except relying party 1. Which means all the other ASNs that are relying on the relying party 1 will invalidate it. We will make our announcement, BGP announcement, RPKI invalid. So there will be no route toward to our IP prefixes. So of course, operating publication points alone do not reveal which ASes are using specific RPs. So what we do is we do internet scanning. So from the prefixes that we own, we send traceroute ping to test connectivity. So let's say if ASN1 was previously able to reach and respond to our network, but cannot do so after the introduction of this test ROA, it suggests, number one, ASN1 highly likely deployed ROV independently. And the second one is AS1 is likely using RP1 for RPKI validation. So in this way, we are able to create a mapping which AS is relying on which RPs and which AS has deployed RPKI. Of course, there are lots of corner cases. So our main focus is to tell whether one AS seems to filter RPKI invalid prefixes. We want to know whether it is due to self-deployed ROV or it is due to their upstream providers. So first example is straightforward because ASN1 uses a relying party 1 and its downstream customer ASN2 uses another relying party. So in this case, because we return invalid ROA to relying party 2, so when he measure the ASN1, it reaches the ASN1. However, AS2, we cannot send any ping. The second case is ASN1 and AS2 shares the same relying party. In this case, it is really hard to tell whether ASN2 also deployed ROV themselves or it is due to their upstream providers, because whenever we send a ping, it will be just dropped from ASN1 and ASN2 as well. And the third case is ASN2 never deployed ROV. The reason why they filter RPKI invalid prefixes, it is mainly due to their upstream providers. So our goal is to disambiguate these two cases. So actually, disambiguating these two cases is not impossible because ASN1, ASN2, even though they share the same relying party, their fetching cycle is different. For example, according to RFC 8210, their default cycle is 600 seconds, but however, these two cycles are not synchronized. So synchronized behavior cannot always be expected. So which means if we, in the T0, we find that we cannot send any ping message to ASN1, ASN2. And then we introduce a valid ROA, the control ROA. And let's say ASN1 has successfully fetched our control ROA. However, ASN2, it doesn't fetch the new ROA yet. So which means in their cache, it still has the invalid ROA. So when we do this measurement, we can see AS1 responded to our ping, but ASN2, no, right? So if we do this measurement multiple times, then what we can observe is the observed ROV status of ASN1 and ASN2 may not always appear synchronized. So this is a strong hint that upstream and downstream, they deployed ROA, they deployed ROV by themselves. The second case is upstream filtering. It is obvious because no matter how many times we do the experiment, we will always see synchronized behavior. So in that case, we can tell AS2 hasn't deployed ROV, they just rely on their upstream. So we've been running this measurement since last year, May. So far, we measured 21,000 ASes. And then we found that 1,100 ASes self-deployed ROV. And also, these ASes rely on 1,600 RPs covering 1,300 ASes. So let me share some observation. The first one is reliance on RPs. We find that 52% of ASes rely on exactly one RP solver. It is much better than not deploying ROV, but slightly concerning because it is because of single point of failure. So RFC 7115, it recommends configuring multiple RPs to ensure resilience. But we found that half of them just deployed, just relying on one RP. And this is another example of how we detect whether it is self-deployed ROV or it is solely based on the upstream customers. So what we do is we keep measuring, we keep sending ping messages to measure the connectivity. And then we deployed these invalid ROAs, and we measure how soon they disconnected. So downstream ASes lose connectivity precisely when the upstream filters. So let's say if lots of multiple ASes relying on same upstream customers and upstream, and if upstream just deploys ROV, then all the customers they lose connectivity for RPK invalid prefixes simultaneously. In case of self-deployment, independent ASes drop at the different times because of the different cycle. Because of that, we can see a kind of distributed pattern. So in this graph, x-axis shows a time to stop responding to our ping, and y-axis is ASN index. So for example, in case of Comcast, they run a private RP. We find that 94 ASes drop simultaneously. It is mainly due to because upstream, because of their customers drop, they cannot reach to the RPK invalid prefixes because it is filtered by their upstream. However, in case of Cloudflare, it runs a public RPs. So client ASes drop at the very times because they deployed their own ROV. So as you can tell in this graph, red dot, it is spread over the timestamps. And the third one is NTT, because NTT has also downstream customers, and also it runs their public RPs. That's why when you focus on the blue dot, it has a straight line, vertical line, but also some other timestamps are scattered. And third one is more about a general behavior of ROV. The top graph shows self-ROV. The x-axis is self-ROV AS sorted by their AS rank. And y-axis is how many customers are protected by this AS's ROV deployment. And also the bottom graph is x-axis is AS rank, and y-axis the number of deployment. So it is quite straightforward. Tier 1 and large ISPs drive global ROV effectiveness, and ROV adoption is skewed toward large providers. And also smaller networks remain vulnerable without upstream protection. So, which means still, even though the network is small, we recommend deploying ROV themselves without relying on their upstreams. The last one is about validation latency. So when you publish ROA, it takes a while to get actually be consumed by ASes for ROV. There are lots of latencies. For example, you publish ROA to RIR, for example, dashboard. Then they have different cycles to fetch ROAs and assign ROAs and upload it to their publication point. And also RPs have different cycles to fetch RPKI objects from repository and validate it. And also routers have different cycles to fetch the VRPs from RPs. So these latencies are merged together. So end-to-end latency it occurs like 60 to 120 minutes. And RP2 router step alone, it adds up to 37 minutes. So the implication is even after ROAS update, operational lag leaves invalid routes alive. So it is something you need to make sure when you tune your ROAS. And also, if you need if you want to fetch, update ROAS much more frequently, you can tune your fetching time. So the summary is RoVista Plus is a framework that goes beyond the RoVista to reveal how ASes truly deploy ROV. We do this by running our own dynamic publication points and the internet-wide scan. And the results will be available, the updated results will be available on this website. The reason why we haven't published the new results yet is because some security concerns. For example, if we just release the mapping between ASes and what RP IP addresses they're relying on, it could be exploited for some security attacks. So because of that, we are still discussing what kinds of information we should release for the debugging or other purposes for network operators. And also, we believe we designed this framework for RPKI purposes, but actually, we think that RoVista Plus is more than just a platform for measuring ROV deployment. For example, let's say there is an AS path 123.777. If we are interested in exploring alternative paths, we can selectively return test ROAs to AS2 only, causing only AS2 reject our announcement so that we can measure how AS1 adjusts to its path to reach us. So by doing so, we believe we can have the kind of broader view of the network paths. And lastly, so we've been communicating with the lots of network operators to deal with ROV problems they face. So if you see some unexpected behavior of ROV, let's say I deployed ROV on my network, but still your website still shows that we haven't deployed ROV, then please email us. We are actively looking for challenging problems and collaboration opportunities. And also, I'd like to highlight that this work is joint work with my students and also my friends at the Cloudflare. And also, I'd like to thank my the sponsors, NSF and the Comcast. Thank you, and I'm happy to take questions.
All right, any questions? Oh, I see some right here.
Hi there. Thanks for the presentation. Tony Tauber from Comcast. A couple of things come to mind. One is you mentioned for us, the results of simultaneous drops suggesting an upstream, and I'm guessing the upstream you're thinking of is our backbone that it serves as the upstream to our various regional networks.
Yes. Yeah.
So I guess that result could be consistent. Another thing is the allowing, citing a lag in basically withdrawal of invalid routes. So I think that's the case where a ROA changes, right?
Mm-hmm.
So, which is interesting, but I think to my way of thinking, the main security benefit of ROV is to keep from misoriginations and hijacks from happening, not necessarily to quickly enforce policy changes. So that isn't as big a concern, really. Some may use it for that purpose, but I don't think that's necessarily it's not saying it's not. I don't think it's proper to think of it as this is like a window of vulnerability. That's just a small net. And then the other thing, last on the RP identification, I know there's some consideration or work being being theorized about, maybe putting RPs behind like a proxy, which would be, would obscure some of those pieces. So something to be aware of.
Yeah, we actually measured one RP keeps changing IP addresses. Yeah, it is.
Oh, you think it's because it's the proxy?
Yeah. So we knew who manages that. So Job Snyder, and he told me that he does so intentionally. So that's a good solution actually. Yeah. So there are some research work running publication point behind the Tor network.
Yeah.
The concern is about the performance. Yeah.
Yeah. Well, okay. Thanks very much.
Okay, any other questions? All right, thank you, TJ, for an interesting talk.
Yeah, thank you.